Hello everyone, this is Khazar Hussain and I'll be presenting Seed Selection for Successful Fuzzing by Adrian Herrera and colleagues published at ISSTA 2021. This paper addresses a surprisingly overlooked aspect of fuzzing, how the initial seed inputs you choose can dramatically affect whether your fuzzer actually finds bugs or not. Let's start with a quick refresher. Fuzzing is a dynamic analysis technique where we feed a target program a large number of inputs, many of which are intentionally malformed, and observe whether the program crashes. If it does, we've likely found a bug or a vulnerability. If it doesn't crash, we move on and try the next input. The beauty of fuzzing is that it's very simple. You don't need a formal specification of what the program should be. You just throw inputs at it and see what breaks. The approach has been incredibly successful, so tools like AFL, LibFuzzer have found thousands of bugs in widely used software. Now, there are two main categories of fuzzers: generation-based fuzzers like Dharma and Code Alchemist, which require a formal specification or grammar of the input format, and then they synthesize test cases from scratch based on that model. Or mutation-based fuzzers, on the other hand, they take a different approach. They start with an initial set of seed inputs, like actual files, and generate new test cases by randomly mutating those seeds. Tools like AFL, HongFuzz, and LibFuzzer fall into this category. This paper focuses specifically on mutation-based gray box fuzzers, and the gray box part here means that they use lightweight instrumentation to collect code coverage feedback during their execution, which guides the fuzzing process towards exploring new code paths. Here's how the gray box fuzzing loop works. You start with a seed corpus, your initial set of input files, and then the fuzzer picks a seed from the queue and applies random mutation to it. It either bit flips, does byte insertions, deletions, splicing two inputs together, and so on. It then executes the target program with this mutated input and collects coverage information. Specifically, which edges in the control flow graphs were traversed. If the mutated input triggered new coverage that we haven't seen before, it gets added back to the corpus for further mutation. If it doesn't discover anything new, it's discarded. This feedback loop is what makes graybox fuzzing so effective. But notice where it all starts: the seed corpus. This is the foundation that everything builds on. And the central question this paper asks is, how should we choose the initial seeds, and does it even matter? In practice, researchers and practitioners use three main approaches for selecting seeds. The first is the empty seed, literally an empty file or a minimal file with just enough inputs or bytes to pass basic format checks. The second is singleton seed, a single valid file representative of the largest input format. And the third largest is large corpus, collecting thousands of files by crawling the internet and then aggregating them together. Surprisingly, there's been no real consensus on which of these approaches is best. Some researchers swear by the empty seed, arguing that it's simpler for a starting point and that it reduces the search space, but others prefer large corpora for a maximum initial coverage. This paper sets out to settle this question systematically. The authors conducted a thorough survey of 28 fuzzing papers published between 2018 and 2021, extending early survey work by Cleese et al. What they found is striking. Seed selection practices vary widely across literature. 8 papers used empty seeds, 9 used valid seeds with known provenance, 7 relied on benchmark provided seeds, and 5 randomly sampled from larger collections. Then 4 manually constructed seeds, and 3 didn't even mention their seeds at all. Cleese et al. Had previously warned that most papers treat seed choice casually, assuming that any seed works equally well. But the evidence shows that that's not the case at all. And yet, even after that warning, the fuzzing community largely continued with the same ad hoc practices. There is also a significant gap between how academia and industry handle seed selection. Academic evaluations tend to use empty or singleton seeds. It's simpler and seems like a fair baseline. But industrial deployments tell a very different story. Google's OSS First service, for example, maintains seed corpora ranging from a single seed up to 62,000 seeds for the Suricata project. The median corpus size across OSS First projects is 36 seeds, with more than half of the projects including over 100 seeds. But here's the thing. The authors looked at Circata's 62,726 seeds more closely, and by removing duplicates, they got it down to about 31,000. And then by applying AFL Seaman, AFL's corpus minimization tool, they reduced it further to just 145 seeds, which is a 99% reduction. All that redundancy in the original corpus was just wasting fuzzing cycles. To really drive this point home, the authors reproduced an experiment from the Red Queen paper. The original evaluation first read readelf, a standard binary analysis tool using an uninformed generic seed consisting of printable ASCII characters. The results show that AFL fast and HONKFuzz covered very little code. But when the authors repeated the same experiment with different seeds, the results changed dramatically. With the uninformed seed, AFL fast covered less than 1% of readelf's code, switched to a single verified ELF file, and coverage jumped to about 38%. And with a minimized corpus of 366 ELF files, it further reduced from 100,000 using AFL Seaman. AFL C++ achieved actually 60% coverage. That's 60 times coverage, or 60 times difference in coverage, just from changing the initial seeds. This is a powerful demonstration that seed choice isn't just a minor detail, and that it's fundamentally shaping the entire fuzzing campaign. So this paper makes three main contributions. First, a systematic review of seed selection practices across both academic evaluations and industrial deployments. Second, Optimin, a new corpus minimization tool that produces provably optimal minimum corpora using maxat solving. And third, a massive empirical evaluation spanning over 33 CPU years, comparing 6 different seed selection approaches across 21 targets and 2 fuzzers. Now let's understand the theory behind corpus minimization. The core idea, first formalized by Abdul Noor and et al. In 2010, is that corpus minimization is an instance of the minimum set cover problem. You have a universe U of coverage points, all which contains all of the edges in the program's control flow graph that any seed in your collection triggers. Each seed covers some subset of these edges, and the goal is to find the smallest subset of seeds that still covers the entire universe U, every edge that was covered by the full collection. This is a classic NP-complete problem, which means that finding the true optimal solution is computationally expensive, so all existing tools, including AFL CMIN and MinSet, use greedy heuristic algorithms to improve their chances. They get close to optimal, but they cannot guarantee it, essentially. Let's look at the two main existing tools. MinSet, proposed by Rebert et al. At Usenix Security 2014, performs a greedy unweighted minimization based purely on which edges are covered. It was evaluated with a black box puzzle called BFF. AFL CMIN is AFL's built-in minimization tool and is probably the most widely used. It takes a more nuanced approach. It considers not just which edges are covered, but also the frequency at which they are hit. Using AFL's binned edge count system, it then does a greedy minimization weighted by file size. The key limitation of both tools is that they're heuristic approximations. They don't guarantee that the resulting corpus is truly minimal. This is where Optimin comes in. The key insight of Optimin is that even though the minimum set cover problem is NP-complete in general, for the specific case of corpus minimization, exact solutions are actually computable in reasonable amount of time. Optimin encodes the minimization problem as a maximum satisfiability problem, maxsat. Here's how it works. For each edge in the program, you create a hard constraint saying at least one of the seeds covering this edge must be included. These hard constraints must all be satisfied. We can't lose any coverage. Then, for each seed, you create a soft constraint saying preferably don't include this seed. The weight of this soft constraint is file size of the seed, so the solver prefers to exclude larger seeds first. Then maxat solver, the specifically eval maxat, then finds the assignment that satisfies all hard constraints while maximizing the total weight of satisfied soft constraints. The result is a provably optimal minimum corpus. The paper also introduces WMOpt, a variant that additionally considers edge frequencies, treating the same edge with different hit counts as distinct constraints. This potentially enables even deeper program exploration. Comparing the three tools, MinSet and AFL-CMIN both use greedy heuristics and provide approximate solutions, like we've said earlier. Optimin uses maxat solving and guarantees optimality. In practice, Optimin produces a corpora that are 9 times smaller than AFL-CMIN on average, and it's faster too, averaging about 2.5 minutes compared to 25 minutes for AFL-CMIN. Now, AFL-CMIN is a bash script, while Optimin is completely written in C++. So that comparison isn't entirely apples to apples and fair in terms of implementation, but the point is that Optimin's overhead is so low that a tool provides exact solutions instead of general coverage. The evaluation is impressively thorough. The authors test across 3 benchmark suites: Magma with 5 targets, the Google Fuzzer test suite with 10 targets, and 6 real-world open source programs. These span 14 different file formats, from images and audio to documents and regular expressions. They evaluate 6 seed selection approaches: the full unminimized collection corpus, an empty seed, a benchmark provided seed, and 3 minimization tools: MinSet, AFL-CMIN, and both Optimin variants. They use two fuzzers, AFL version 2.52b and AFL++ with compare log instrumentation. Each configuration runs 30 independent 18-hour trials. They emphasize that 30 trials because individual fuzzing runs very widely and you need that many to draw statistically meaningful conclusions. So all in all, this amounts to around 33 years of fuzzing. For the collection corpus, the authors built web crawlers that ran for 72 hours per file type, collecting from sources like Google search results, Wikimedia Commons, the Internet Archive, GitHub repositories. So all in all, they gathered nearly 2.9 million seed totals. After pre-processing, removing duplicates by MD5 hash and filtering out files over 300 kbs, they were left with about 1 million seeds. This pre-processed collection was then fed through 4 minimization tools to produce the test corpora. They measured success three ways. First, direct bug count, actual unique bugs found with manual triage for real-world targets rather than relying on stack hash deduplication, which is known to both overcount and undercount bugs. Second, bug survival time or RMST, restricted mean survival time. This uses Kaplan-Meier survival analysis to model how long each bug survives before being found. Lower RMST means that the bug is found faster and more reliably. This handles the censoring problem where some trials never find a particular bug. Third, code coverage, specifically LLVM COV's region coverage metric, which is more granular and accurate than AFL's internal edge coverage, which suffers from hash collisions. For RQ1, their question is how effective is corpus minimization? The results are dramatic. Take Popular for example, a PDF library. The full collection has nearly 100,000 seeds. AFL Seaman reduces that about to 2300, but OptiMin's WOP produces just 222 seeds, covering the exact same edges. Across all targets, WOP produces corpora that are on average 9 times smaller than Seaman, and it does so in about 1/10 the time. Minset performs similarly to WOPT in corpus size, typically just a few seeds larger, which makes sense since both look at the edge presence rather than frequency. The Seaman corpora are also consistently larger among the minimized outputs because AFL Seaman treats different edge hits counts as direct coverage points, resulting in more seeds being retained. Now for the most important question, do minimized corpora actually find more bugs? Across all benchmarks, 78 bugs were found in total, 26 in Magma, 15 in FTS, and 33 in real-world targets. The key finding is that minimized corpora consistently outperformed both empty seeds and full corpora. The full corpus is particularly problematic. On targets like Goetzilla, where the fuzzer achieved less than 1 execution per second with the full JPEG corpus of nearly 120,000 files, the fuzzer literally couldn't finish a single pass over the corpus in 18 hours, let alone perform any useful mutations. The minimized corpora found bugs reliably and efficiently, with the specific minimization tool being largely inconsequential. What matters is some minimization happened. Interestingly, the paper also found two magma bugs that had never been found by any fuzzer in prior evaluations, including campaigns totaling over 200,000 CPU hours. These bugs were only discovered using minimized corpora with AFL. Thirdly, iteration rate, the number of text executions per second, turns out to be very crucial. With the GWT ZLI target, the full corpus achieves less than 1 execution per second because the fuzzer is spending all of its time reading and processing the 120,000 seed files. It never gets to the actual mutation and exploration phase efficiently. The empty seed, by contrast, achieves over 229 executions per second. The minimized corpora sets in a sweet spot, 2 to 5 executions per second. Fast enough to make progress, but starting from a much more informed position than the empty seed. This illustrates why simply collecting more seeds isn't better all the time, and that redundant seeds clog the queue and waste cycles that could be spent on more productive mutation. The empty seeds presents an interesting paradox. Of the 41 bugs it found, it was the fastest to find 21 of them, including the 3 CVEs in the SOX audio tool. It also found a known infinite loop bug in libtiff that the other corpora missed entirely. Because the empty seeds mutation could construct a malformed directory structure from scratch, while mutations of the valid TIFF files tended to break the existing structure in ways that caused early parser rejections. But the empty seed also had the highest false negative rate. It's the most likely to miss a bug entirely. On structured formats like XML and PDF, it covers less than 2% of the code because it simply can't synthesize the complex structural elements needed to get past the initial parsing stages. So the paper's recommendation is very nuanced. Use minimized corpora as your primary approach, but consider running an additional campaign with the empty seed to quickly catch shallow bugs. However, never rely on the empty seed alone for industrial scale fuzzing. For code coverage, the pattern is clear. The empty seed consistently explores the least code. on average about half as much as the other approaches. The gap is especially stark on targets with highly structured inputs. For Poplar, for example, empty covers only about 1.5% of the code, while minimized corpora achieves over 41%. Among the non-empty corpora, the four minimized approaches and the full corpus achieve broadly similar coverage, with the minimized corpora often slightly ahead. The key insight is that after 18 hours, the mutation engine can explore a lot, but it needs a reasonable starting point. Starting from nothing is just too big of a handicap. Another interesting finding is that AFL doesn't consistently outperform the regular AFL on coverage where both start from minimized corpora. This suggests that with good initial seeds, faster iteration rates may matter more than just algorithmic sophistication. The real-world campaigns yielded 7 new CVEs across 3 targets. In libtiff, they found an integer overflow that only manifests on a 32-bit system. In Popular, a heap buffer overread, and in SOX, 4 integer overflow bugs and a stack buffer violation was found. Beyond these 7 CVEs, they found another 26 bugs that were already under investigation. The point here is that this wasn't just a theoretical exercise, and that careful seed selection led to discovery of real, previously unknown vulnerabilities in widely used software. Let me summarize the key findings. First, minimus corpora outperforms simple empty singleton and full corpora for bug finding, and that this is the paper's central result. Second, the specific minimization tool matters less than actually doing the minimization itself. Whether you use MinSet, AFL-CMin, or Optimin, the fuzzing outcomes are statistically similar. However, Optimin does produce significantly smaller corpora, which is advantageous and more efficient. Third, the empty seed is a double-edged sword. It is fast for shallow bugs but unreliable for deep exploration. Fourth, the full unminimized corpus is actively harmful on targets with slow iteration rates. The fuzzer wastes all of its time on redundant seeds and doesn't do anything productive. And finally, the paper strongly recommends that seed selection be carefully considered and explicitly documented in all fuzzing evaluations. You should never evaluate a fuzzer with only a single seed, as this can lead to misleading conclusions about the fuzzer's effectiveness. Now for some critical analysis. On the strength side, this paper excels in experimental rigor. 33 CPU years of fuzzing and 30 repeated trials per configuration is far beyond what most fuzzing papers attempt. The use of manual bug triage instead of just stack hash deduplication is more labor intensive, but it is also far more accurate. The statistical methodology is sound. Survival analysis with log rank tests for bug finding and man-Whitney U-tests for coverage. That's good. The paper also has real-world impact with 7 CVEs found, and the authors open source both Optimin and all experimental artifacts, enabling reproducibility. On the weaknesses side, though, the study only evaluates two fuzzers, AFL and AFL++. It's unclear how the results would generalize to fundamentally different fuzzers like Honk fuzz or Live fuzzer, let alone hybrid fuzzers like QSYM. The 18-hour trial duration, while following established guidelines, might be too short to reveal the impact of seed selection on very deep bugs. And then corpus minimization based solely on edge coverage is acknowledged as lossy compression. It may discard seeds that trigger interesting program states not captured by edge coverage. The paper doesn't explore alternative coverage metrics for minimization, which is a slight bummer. And then the quality of the web crawled collection corpus itself is variable. Different crawling strategies or sources could yield entirely different results. The paper opens several promising research directions. First, for example, exploring corpus minimization with coverage metrics beyond edge coverage. Context-sensitive coverage or path-based metrics might preserve more useful information. That is very interesting. Second, evaluating more fuzzers, especially hybrid approaches that combine mutation and symbolic execution in this environment and this scenario, might yield interesting results as well. Third, investing whether we can predict seed quality before fuzzing. Could machine learning models help here with selecting the most promising seeds from a large collection? That's also very, interesting and something that I would personally want to look at. And finally, fourth, dynamic re-minimization during fuzzing campaigns as the coverage landscape evolves. The takeaway from this paper is simple but very important. The choice of seeds is a critical decision that significantly impacts fuzzing outcomes, and it's one that research community tends to, treat too casually, far too casually actually. The recommendation is also very clear. Collect diverse seeds, minimize them with a tool like Optimin, and then always document your seed selection methodology. This one simple step, which happens before you even start fuzzing, can be the difference between finding real bugs and wasting a significant amount of CPU years on doing nothing. That's it. Thank you so much for listening, and I'm happy to take any questions in the comments. Thank you.